Have you ever thought about the force that keeps you glued to your chair right now? It's gravity, the invisible hand that holds our world together. Every morning, when your feet hit the floor, that's gravity. When you pour your coffee and it flows perfectly into your mug, that's gravity. It's so fundamental, so constant, that we often forget it's even there, but our entire existence is shaped by it. Our bodies are masterclasses in adapting to gravity. Our bones are dense, our muscles are strong, all to fight its constant pull. Astronauts in space experience muscle atrophy and bone density loss because they're freed from this relentless force. It's the silent personal trainer we've had since birth, sculpting our biology without us ever noticing. Think about it. Every step you take, every jump you make, is a negotiation with the very planet you stand on. But gravity's influence isn't just personal, it's cosmic. Look up at the night sky. The moon orbits the Earth orbits the sun, and our entire solar system gracefully dances around the center of the Milky Way galaxy. None of this would be possible without gravity. It's the cosmic architect, pulling together gas and dust to form stars, and corralling stars into magnificent galaxies. It holds colossal clusters of galaxies together across unimaginable distances, weaving the very fabric of the universe. For centuries, we've tried to understand this mysterious force. It all started with an apple. Sir Isaac Newton, watching one fall from a tree, had a revolutionary idea. What if the force pulling the apple down was the same force holding the moon in orbit? He gave us the law of universal gravitation, a mathematical key that unlocked the movements of the heavens. For over 200 years, Newton's laws were the final word. They were elegant, powerful, and they worked, but then a new genius came along. Albert Einstein looked at gravity and saw something entirely different. He imagined that space and time are not separate, but a single, four-dimensional fabric, spacetime. And what does mass do? It bends this fabric. Imagine placing a bowling ball on a trampoline. It creates a dip, a curve, and now roll a marble nearby. It doesn't get pulled by the bowling ball directly. It follows the curve in the trampoline. That's gravity, according to Einstein. It's not a force, but a consequence of geometry. The Earth isn't being pulled by the sun. It's following the curve in spacetime created by the sun's immense mass. This isn't just a beautiful theory. Einstein's general relativity has real-world consequences we use every day. Your phone's GPS, for example, wouldn't work without it. Satellites orbiting Earth experience time slightly faster than we do on the ground because they are in a weaker gravitational field. To give you accurate directions, your GPS has to constantly correct for this time difference predicted by Einstein's equations. Without relativity, your GPS would be off by several miles every single day. Einstein's theory also predicted some of the most extreme objects in the universe, black holes, regions of spacetime so warped by gravity that nothing, not even light, can escape. For decades, they were just a mathematical curiosity, but now we've seen them. We've even detected the ripples in spacetime gravitational waves created when two massive black holes spiral into each other and merge. These waves, predicted by Einstein a century ago, travel across the cosmos, carrying the story of a violent, cataclysmic event. Hearing that chirp in our detectors for the first time was like hearing the universe speak. We've come so far, from an apple to colliding black holes, but the story of gravity is far from over. In fact, we're standing at the edge of a new, profound mystery. Einstein's beautiful theory of general relativity works perfectly on the grand scale of planets and galaxies. But when we try to apply it to the tiniest scales, the quantum world of particles, the math breaks down completely. It gives us nonsense, infinities. The two pillars of modern physics, general relativity and quantum mechanics, don't speak the same language. It's the biggest puzzle in science today. What is gravity at the quantum level? Is it made of particles, hypothetical gravitons, that we just haven't found yet? Is spacetime itself made of tiny, indivisible quantum loops? Or is gravity an illusion, an emergent property of something even deeper and more fundamental? Scientists are exploring wild ideas. String theory suggests that all particles are just tiny, vibrating strings, and gravity is one of their vibrational modes. Other theories propose extra dimensions of space that are hidden from us. We're looking for answers in the heart of black holes and at the very beginning of time. the Big Bang. These are places where gravity is both incredibly strong and operating at quantum scales, the perfect laboratories to test our new ideas. So the next time you drop your keys or feel your feet firmly planted on the ground, remember the grand journey of this force. It's the everyday anchor and the cosmic sculptor. It's a solved problem from the 17th and 20th centuries, and the greatest unsolved mystery of the 21st. We've peeled back layers of understanding, from Newton's pull to Einstein's curve, but the deepest nature of gravity still eludes us, hiding in the quantum foam, waiting to be discovered. The adventure is just beginning. Thanks for watching. Subscribe, like, and share.